that the scheduling has two parts really to it. One is sort of the mechanisms for actually implementing scheduling, which we're going to mostly focusing about. And of course, there are policies about how to choose from a number of runnable threads which actually one you should pick, which actually we'll talk very little about, but then I'll say something about it. But before doing that, let's first jump into, I guess, the homework for today, and just make sure that we understand what the answers are. And I guess somebody in the class actually seemed to have won the lottery by triggering a race condition that I thought was pretty hard to trigger. But so first, so the context for this is the homework related to locking, and particularly the interaction. Look at the homework. Look at the interaction between locking and interrupt handling. And so the first question was related to the IDE read-write. Correct? This is the function that actually is the interrupt handler that runs when an disk interrupt comes in, and it does a bunch of different. It looks at the queue. Actually, this is the function that starts, the disk read and write operation. And so the first thing it does is actually requires these IDE lock, and then it does a bunch of stuff, looking at the queue, sticking things into the queue so that they can actually be delivered, to the disk. And then the start job, runs this function ID start, where actually gives the disk a kick to sort of start looking and doing something. In particular, it will issue a disk write or read, and then at some point the interrupt will come in and finish off, that disk read or disk write. And so the function here just waits for a while to until actually the disk operation has completed, because the disk is a slow device, which it might take a little while to do it. So I'll talk a lot more about sleep and wake up next week, so I'm not going to focus on that. But here then the final call is release, which releases the IDE lock. Right? And as you've seen, the lock does acquire an IDE lock, do a couple of interesting things. And one of the things it does, it actually disables interrupts. Right? Acquire disables interrupt, and release re-enables it. And so in this section between acquire and release, correct, the code runs in sort of, there's two forms of automaticity going on at the same time. First, the form of automaticity is basically the locks themselves, which assure basically isolation or automaticity with respect to other cores or other CPUs. So two CPUs call at the same time IDE read and write. One of them will grab the lock, and the other one will be spinning. Correct? If you've seen the spinning lock implementation in the last lecture, the other one will be spinning and waiting until the lock is released. Right? So that assures that there's no other cores actually entering this piece of code. Now the problem with this piece of code is that there's the same CPU can actually enter this code too. Right? And so the other way that is actually what we need is automaticity with respect to the same CPU. You might wonder, like, well, that's strange, correct? Like, didn't this CPU grab the lock? So how is it possible that any other piece of code can actually run in this CPU, right? And the answer is, what can happen is there are interrupts. And if you don't do anything special on the acquire or release, then it could be the case that in one of these atomic sections with respect to other processes where an interrupt might happen on the current processor and basically run in the middle of this atomic or critical section, right? And so to see whether this actually was a real problem, the homework asks you basically to insert after acquire STI, right, which actually enables the interrupts, and then before release clears interrupts. And so that basically sort of models a world where acquire and release were actually not doing anything with interrupts. So it counters or cancels whatever acquire and release are currently doing with interrupts, just to understand what goes wrong. Right? And so what goes wrong? Yeah, go ahead. Yeah, what happens is, let's say, the processor runs, acquires the lock, you do enable interrupts, correct? Then of any, you kick off the disk function, correct? The disk function at some point is going to generate an interrupt saying, hey, I'm done, correct? And so, and if that happens before the release, then basically what will happen is, correct, that disk function will also, call an interrupt, we'll call the disk interrupt function. If you look at the disk interrupt function, one of the first things it does is grab the IDE lock, right? And it has to do that because it is going to manipulate one of the shared data structures. Right? And in principle, the interrupt could have run on a different processor, and then the locks would have ensured that there was atomicity. But if they run on the same processor, the locks don't really ensure atomicity. Right? In fact, this would be, we flag this or require release flag this as a deadlock because the same processor is asking for the same, the same lock twice. Does that make sense? And so basically what we're seeing, there are two mechanisms to get actually atomicity with respect to, two mechanisms to get atomicity. One is using locks, and basically using this atomic instruction to sort of set the lock. And the other one is actually clearing and enabling interrupts. And the x86 implementation of require and release basically does both. Right? It guarantees atomicity with respect to other CPUs, but it also guarantees atomicity with any interrupt handler that might run on the same CPU. Make sense? So then the second question was related to via alloc, and where you were supposed to, same as here, do a store interrupt and a clear interrupt. And the question there was, well, why, and as you probably noticed, nothing actually really goes wrong, except for one person who did get something wrong, which we'll talk about in a second. But I think most people presumably observed, actually, for most, who did actually observe anything go wrong? Everybody just worked out fine, right? Doesn't matter that you actually have those sphere in. So why is that the case? I just explained to you that there's a danger, correct, that if you re-enable interrupts, an interrupt handler might run. So it is the case, correct, as soon as we store interrupts, we enable interrupts, and it is the case that this code between acquire and release might not run on atomically, correct? Even though the instructions like one by one, you should think about this, that between any two instructions, there could be another piece of code out of the other side of the operating system that you're running, correct? I'm sure you're going to be very aware of this during log 4, correct? Where you're going to look at two instructions and say, well, this instruction follows the other instruction, so they must be executed, one after the other. And the answer is no, they're not, correct? There's no guarantee that actually will happen. In fact, it might be very likely that there's an interrupt handler coming exactly between the two instructions and it runs off with a whole bunch of different pieces of code in x86 or in JOS, correct? So the first thing you need to do when you think about concurrency and interrupts is that you should get out of your model of the world that basically, one, two instructions follow each other, they run after each other immediately. That's just not true. And so, so I'm making a passionate case for the fact that this code looks to be wrong, yet nothing bad happened.
The lock is used in the interrupt handler.
Yeah, there's no other interrupt handler. The answer to this question is exactly as you point out. There's no interrupt handler that actually grabs this lock, at least not immediate. And so, now one of you, I don't know who, sent me an email saying like, hey, I won the lottery. Right? If you read the homework assignment very carefully at the end, we said something along the lines of, it's still possible that something goes wrong and that you will see a panic. And so you got that panic. I'm quietly impressed with. The person here? Oh yeah, that's too bad. And so how is it possible that there still could be a problem?
There is a code path that does try to get the ftable lock.
Yeah, and so how would that code path work?
I think it was in the process exit thing.
Yeah. Okay, so why did actually this will become much more clear when we go through the lecture and where actually the risky point is. And so we'll understand that. I'm not going to give you the way yet, but like during the lecture, hopefully we'll figure out where there's an area. Yeah, go ahead.
There's an interrupt and it switches to another process, and then runs that one down and has a system call.
Yeah. So that we want a possibility, correct? So there are actually multiple ways of this going wrong. And so one obvious one is that you're running, correct, and you enable interrupts, and the clock interrupt goes off, right? And the clock interrupt says like, okay, you got to yield, the processor to some other thread, right? So the x86, faithfully, gives another thread to run. That thread might be in user space, correct? Doing, calling a new system call like create file or something, and that will may in the end call file alloc, and that might actually then acquire the same lock, right? And then we have a deadlock. So that's one scenario there. That's probably not the one, actually, yeah, go ahead.
If multiple locks out at the same time.
Sorry?
If multiple locks out at the same time, this will correct all of that.
Okay, no, so let me come back to it. We'll see when we get. So there's a little bit, it's a little bit slow, but it is possible. Okay, any questions about this so far? Okay, let's then talk a little bit about processes. And just to remind you, this sort of comes back to one of the very early points of 6828, right? Like the whole idea of an operating system, or one of the main goals of an operating system. We have the operating system, and we have different applications running on them. Let's say some server, whatever, Emacs. And what we want is isolation between these applications. Right? We want isolation between the application, and we want isolation between the applications and the operating system. Those are the main sort of goal. And we're sort of basically take little detours and explore from one way of getting isolation, and then come back and look at another aspect of isolation. And so the particular isolation aspect we want to look at today is how processes are isolated from each other. Right? And there are a bunch of different components to that. And some of them we already looked at, but it's part of the work I have to quickly talk about. So the main idea of a process, one way to think about what a process is sort of an abstract virtual machine. It's provided by the operating system. And I'm not meaning a virtual machine in the form of like whatever the Java virtual machine or like VMware, but just the idea of a virtual machine as in the literal sense of the word, or the abstract sense of the word. So what I mean is like every application can think as if it has its own machine. Right? There are multiple machines, maybe on this virtual machines in the same processor, but the application has the notion or the idea that it actually has the whole machine to itself. And doesn't really have to worry about any other applications that might be running on it. And that's sort of a great stepping stone for getting isolation. And we're already seeing a good part, the mechanisms to get isolation are working. One part is the virtual memory part, right? Where every application has its own address space. So it's even not possible to refer to address locations from other applications unless it's set up explicitly, right? And so VM gives us a lot of good mechanisms to at least separate the address spaces of different applications out of character. And we talked quite a bit about VM, right? In fact, now if you've done Lab 3, you're like experts on implementing virtual memory. And in fact, in Lab 4, we'll come back, much more probably harsh than in Lab 3 when you're doing the copy on the right fork. So that's one aspect, right, that we focus a lot about. Now what we want to focus on is the aspect of actually making sure that if we have more applications and we have a small number of processors, how do we actually get the multiplex of multiple applications on a small number of processors? And so let's say we have two applications in one processor. Right? We now have to provide these applications with the illusion that they can just run happily. It doesn't really matter if there are 2, 10, or other processes on the machine. Maybe performance-wise it might matter, but at least they should feel like they get some forward progress. They're not being slowed down. They're not. Another application can't stop them. Right? And the key risk, is the multiple risks. But the key risk is, for example, this server sits in an endless loop. Right? It just consumes the CPU, doesn't do anything useful, never releases the CPU, and so we want to arrange it that even if that happens, that this other application can actually make forward progress. Right? That's the goal that we're trying to achieve. And we're going to look at the mechanism for that, making that happen. And we saw bits and pieces of it, but we're going to look a little bit more in detail. Okay, so let's talk a little bit about this. What is that actually, the API that goes along with processes, to get a little bit of better handle on actually what are the abstractions that we need to implement. or a bunch of abstractions that constitute sort of the process side of the virtual machine. So clearly, we know about fork, the ability to create a new process. We know about exec, because we've seen that in action. The ability to actually overlay your current process with a new image so that you can run a new program, correct? And so, but there's a bunch of other calls. What are some other calls related to processes? Many of which you will implement. Sleep, we'll talk a little bit about it, although it's not sort of visible in the Unix API itself, correct? It sort of sits internally. So we'll talk a little bit later about it. Yield, I guess, is similar to sleep. But let me actually write them down. They're definitely related to, yeah.
Exit?
Yeah, exit is that's the one I was thinking about. If you just think about it again from the sort of Unix shell, like you implement a Unix shell, which system calls can you make to manipulate processes? What are, so, yeah.
That's great.
That's great, correct? Large memory. Talk quite a bit about that. Any other calls? Should be more, if you think about the shell, you know. Yeah, wait. Yeah, you can explicitly direct wait on another process, and this is very common, correct, where the parent wants to work and wait on the child until it's done before it proceeds. And clearly implemented with some mechanism like sleep, but we're going to talk about that actually on next week quite a bit in detail. So this is actually quite an interesting topic. Any others? There's one crucial one, right? Like what happens if like somebody actually one process sits in an endless loop? What do you like to do with it? Kill, yeah. Kill. User or whatever the shell, or the other applications you'd have to control as a user should have control of the ability to actually stop another process. Okay. All right. So those are the main ones, and we'll see all of them in action. Okay. So now let's go back to the key problem that we need to solve. Okay, so we're trying to get isolation, and in principle, isolation would be easy, correct, if there were more CPUs than there were applications, because we give every application its own CPU, and then we have to worry about the infinite loop at all. And so that would be a trivial way of solving that problem. But generally, presumably, we don't want to limit the number of processes by the number of processors that we have. And so we want to be able to deal with the case where we have more applications than processors. And so that's the problem that we want to solve. And so the way we're going to think about this is that every process has a thread. And what we want to do is, and so the thread, what is a thread? Actually, a thread is a shorthand for thread of execution. And really what it boils down to, and that's sort of a recursive definition, right? The thread is a thread of execution, but really what it boils down to, it has sort of two primitives. The ability to stop a thread and then restore the thread later. And the ability to stop a thread basically means saving all the state that's necessary to at some point later resume that thread. Another way to think about a thread is basically a running program. You start a program that runs for a while, and you can do two operations on it: stop and then later resume it. Right? So stop, resume is the main sort of API. And so now you might wonder, okay, what is the relationship between threads and processes? In early Unixes, these terms were actually interchangeable use because they didn't really mean that much different. Today they do mean quite a bit different because it's often the case that the user level process might actually have multiple threads of execution. So within the process, there might be multiple threads of execution. And so one way to think about what a process is basically a virtual memory and address space plus some number of threads. And it might be 1, it might be 10, it might be many. Right? And so what we're going to be focusing mostly today on is not on sort of the address part of the process, because we're going to talk about this endlessly in the last couple of weeks. But we're going to mostly be talking about the threading side of the process. Now, in XV6, and as well as in JOSH, your this distinction is slightly is not as clear because basically we're always running with one thread in user space, like many early Unix implementations. Now, luckily, there are examples in x86 of actually multiple threads in the address space, because like every user thread, what does it have? It has a corresponding kernel thread, right? The kernel stack, we call it. And so one way to think about it in x86 is there's a server, there's an application thread, and corresponding to every user level thread, there's a kernel thread. And why was there a separate kernel thread for every user application? Waste of resources. Is there any good reasons?
It has to access their address space.
Yeah, can't always trust the user level thread of the operating system writer or the state of the user level thread.
Keep it isolated in case they pull up their stack or something.
Yeah, we can't really trust. So a thread typically has its own stack because otherwise you can't actually store or save for program execution, right? Because the stack has all the procedure calls that are sitting on all the stack frames that constitute the current state of the program. And we can't really trust, back to isolation, we can't really trust the user stack. And so in x86, we have a separate stack to actually take system calls on. And the same is true in JOS, right? Except you're not having multiple, you only have one. And so in x86, every user level thread has a corresponding user level thread. And so in fact, in the kernel address space in x86, there are many, many threads. One for every application, right? Does that make sense? And so we're going to be context switching between threads in the kernel. Yeah. Right.
Could you just explain what would go wrong if you tried implementing it with only one kernel thread?
Okay, well, we'll come back to that actually. It turns out there's a bunch of heartbeats related to x86, mechanisms, right? Like when you do a system call and you change from one address space to another, from one CPL level to another CPL level, then the hardware mandates that you set a stack up to actually receive that system call. Right? And the reason the hardware mandates is because it can't trust whatever was in the stack pointer value in user space. Because the user space stack might be like, maybe there's a 0 in it, or like there's no allocated memory for that particular stack. But remember, actually, we played this trick where we do guard page below the stack, so that when actually the stack overflows, you get actually a fault. And so if the kernel were to use the user stack, right, at the point that the fault would happen, there's nothing you can push. There's no stack to push anything on, correct? So the kernel has to have its own separate stack to actually push things on. And so then, if the kernel has to have its own stack at all, anyway, you're basically mostly there in terms of actually implementing a thread, because the thread actually contains most of the execution, or the stack contains most of the execution. And so that's a small step to then say, okay, well, there are user threads and kernel threads. Make sense? And in JOS, you're going to do this slightly differently. Like, how many threads are there in JOS in the kernel? It's going to be one. It's going to be one per CPU, to be precise. And the reason is, like in JOS, basically the kernel is so small, we never run really threads for it. We never run computation for a long period of time. There's no notion that actually the thread in the kernel might block. While in x86 this is possible, and therefore we have to have a separate thread per user thread. Make sense? Okay. And so the way, now, so our main goal is basically going to ensure, or our main goal is going to be like figuring out how to sort of multiplex these multiple threads of execution. In fact, we already have 4 of them, right, on a single CPU. And so and there's a couple challenges in doing it. Let me break in the main challenges are. There's a bunch of goals and a bunch of challenges. So start with the goals. One, we want to switch transparently. So the kernel, since this server thread might be in an infinite loop, the kernel wants to be able to transparently switch between two applications, without the applications really noticing, other than maybe a good measure that they didn't get the CPU for a period of time. But in principle, in terms of like correctness, the program will make forward progress maybe a little bit slower than expected. So we want to be able to switch between them transparently without actually the application having to tell the operating system what you would be aware of. So that's one goal. And the second one, we want to make sure that a thread cannot hog CPU. Because if it could, then we didn't get our isolation. And we'll see, just to be a little bit more precise, this goal, the second goal, we generally try to achieve only for user threads, and not for kernel threads. So, our assumption is basically that the server or user threads going to run code, correct, that are written by some programmer who knows, like whether he's capable or not. But the kernel threads, correct, are implemented by the kernel developer. And we're going to assume that the kernel developer is an expert programmer and doesn't actually write code that has infinite loops. Right? And so there's no reason for us, and you do that in JOS and you do that in x86, there's no reason for us really to be worried too much about infinite loops in the kernel thread, because presumably what will happen, correct, the operating system won't work anyway, and we will have to fix it. So it's abundantly clear, correct, that is a problem. So we're mostly going to be focused about worrying about user level threads that are hogging the CPU and transparently switching between them. Does that make sense? Okay, so then the basic solution to this plan is as follows. Just to sketch this out. And we've sort of seen it a little bit already in action. We've got our application thread, we've got our other application thread, and the way we're going to basically play this game and to make sure that it's transparent and that the thread cannot hog the CPU is that we're going to set up the timer chip. We've seen it before. We're just going to generate a clock interrupt every, say, 100 milliseconds. Right. So let's say we're this particular user level thread, and we're in an infinite loop. What will happen is the timer interrupt will go off. And so what happens when the timer interrupt goes off? Well, we're going to switch, right, at that point from the user to the corresponding kernel thread. Right? See these multiple times in action. And so now at this point, we have an opportunity, correct? Because the kernel thread is written by the kernel developer. And so one of the things that the kernel thread can do is to say, like, oh, I'm happy to give up the CPU at this particular point in time. Right? And this is like the call that we saw before, where the kernel thread calls yield to basically give up the processor. And so at the point that the kernel thread does a yield, and then switches to another thread, correct? The scheduler is then the entity that looks at like the number of available threads and decides, okay, I'm going to run to another thread. So it might take some other kernel thread, switch to it, and so we look at the detail to the mechanism for switching, correct? This is context switching mechanism that we looked at, but we'll go back over it again. Switch to another kernel thread, and that kernel thread we can now basically return, as it did before, out of the system call with red eye to the user level, another user level process. Right? And so this gives us the basic two goals. We're switching transparently. The application is actually not aware that this section switch is happening. The kernel is arranged behind the background. And we also arrange that the program cannot hawk the CPU. It can hawk the CPU during its time slice, correct, and during the period that it is allowed to run, but but it doesn't stop anybody else from running. And this is good enough, correct? Even though like maybe the CPU or the thread could hog its CPU for the complete 100 milliseconds, at some point control will be given to some other process, and that may be, for example, the shell, and the user can type in kill to actually get rid of the process that actually be hogging the CPU. All right. Okay, so now, so this is the basic plan, and this plan sounds pretty straightforward, right? I mean, like, how could it be complicated? Well, it turns out it's sort of complicated for a couple reasons. So let me write down those challenges. So the first problem that will show up is that we're going to look into the details of this code is changing from one processor, one kernel thread to another kernel thread. This code tends to be sort of opaque. And the meaning of that is like hard to understand. And in fact, early Unixes, one of the first Unix, actually where x86 was based on version 6 Unix and version 7 Unix, had this famous quote in the kernel code, correct? And actually, in exactly this point of the context switching, where basically the code, where the comment next to it was, "You're not supposed to understand this." And so, you know, of course, this is a very dissatisfying answer for people that take in an operating system class. You are supposed to understand this, and so we're going to walk through and make sure that you understand this. But it tends to be tricky code because, like, you know, you're manipulating machine state. You know, you've done this quite a bit of now, so for you it's not going to be that difficult to understand it. But like, and if you look at it the first time, it's sort of like magic. It seems to work, but like not clear why. But we want to make sure that we understand it. The second challenge is that there's concurrency. And you know, I drew the picture as if there's one CPU here, but in reality, we want to make this stuff work also in the case when there are like 2 CPUs and maybe 3 apps. Right? And so we want to be able to have one processor context switch, another processor context switch correctly too, and we want to be able to run the scheduler in parallel. But you know, of course, now we know all about blocks. You know, this is dangerous, correct? Because the scheduler is looking at some shared data structure, namely the proc table, which lists all the runnable processes. And we better make sure that actually works out correctly. And this turns out to be, in the case of thread switching, even more challenging than you've seen before in the last lecture. Because in the last lecture, basically, you know, the general scheme is that the thread that acquires the lock also releases the lock. But that is not going to work for us that well here, and I can sketch you out why. Is because if we're doing this context switch, during this context switch, we're going to change the status of this thread or this process, right? But we don't want any other process to look at that state yet. So we have to acquire the lock before we do the thread switch and release it after we're done with the thread switch. And so this is an unusual situation where basically one thread acquires the lock and then another thread actually releases the corresponding lock. And that makes it harder to reason about correctness. Right? That was going to make this challenge of dealing with concurrency a little slightly harder. And we'll see in a second how x86 resolves this. And then the third problem, which often is a problem in an operating system, is just cleanup. So if one thread terminates and exits, we need to reclaim its resources, which I think we want to basically put the page that corresponds to the stack back into the free list of pages. Right? There's a little bit of a problem with doing that, because if the current thread is running, right, and it says, okay, no, I'm exit, I'm done. Well, it's still running on its stack, right? So we can't free its stack at that particular point in time because it's still running on it. And so how do we deal with that? And similar with kill, it's actually a little bit tricky to actually get this right, because let's say the threads are running on a processor, right, like in the infinite loop, and I want to kill it. Well, and I'm running on another processor, right? I want to send a kill signal to that thread. Well, I can't just clean it up, right? Because it's still sitting in the processor and it's actually running. And so we have to have some mechanism to get control over that thread, to actually clean it up. And so we'll see that a lot of the complications come from cleaning up. Does that make sense? So the basic plan is simple, but then, of course, like in any sort of 8-to-8 topic, like if you look at the details, it turns out it's annoying. And so this is definitely the case too. So we're going to look at x86. Let me see talk quickly about how x86 basically deals with these challenges. And of course, like the issues are going to be similar in JOX, but fortunately a little bit less complicated because there's no multiple kernel threads. And a lot of the state related to the operating system sits in library operating systems anyway, which simplify a bunch of things. So the first thing that x86 does actually is when switching from one user level thread to another user level thread, it actually doesn't switch from the corresponding kernel thread directly to the other kernel thread. In fact, the way it actually works is there's a third thread actually in the picture, which is the scheduler thread. And so when an application, one user level thread switches from this to another, it will switch into the kernel, to the corresponding kernel thread for that application. Then it will switch to the scheduler thread. The scheduler thread will run around in the proc table and look for which is the next thread to use or run, and then switches to that thread. And so basically every user level switch results basically in 2 kernel level thread switches. And you might ask, well, that seems stupid. Why not go straight from it? You're going to know that you're going to select this thread. Why don't you go straight from there? And it turns out that has to do partly with cleanup. So one problem, so let's say there is actually no thread to run anymore. Okay, so this thread wants to switch out, or maybe it's done, and there's actually no thread to run anymore. We still need to clean up that thread, correct, in some way. We want to take it to the pages back and all that kind of stuff. And so it's just inconvenient. We can't, if the current thread exits, there's no other thread to run it. There's no other thread basically to clean it up for it. So this makes things complicated. And in fact, if you look at many operating systems, there's a lot of tricky code there. And the way x86 makes this a lot simpler is to say, well, there's always one thread running, or available to run, that can do the cleanup or do any other stuff. And so per processor, there's always one scheduler thread. And you can always switch to that scheduler thread. And that scheduler thread can do anything it likes, to clean up or garbage collect or whatever. And so there's never a worry that what happens if I'm done and there's no other thread to run. What do we do next? All right. The downside of our solution is, because it's much cleaner. We flowed it, hopefully it's easier to understand. The downside of our solution, of course, is we're paying 2 thread switches for every thread, the usual thread switch. But clearly you can optimize this, and then of course you get complicated code, and we don't do that. So we want to make sure that you understand. Okay? So that's one trick, one mechanism that's used. The second thing that's going on is that when 2 kernel threads switch, so these are kernel threads, kernel thread 1, kernel thread 2, and here's our scheduler thread. The style and the way they switch between them is actually very stylistic. It's not a random pattern. Actually, there's only basically there's one piece of code where you call whatever it's called, switch. And so if a kernel thread wants to transfer control to another thread, it calls a switch function, and that switch function actually resumes the scheduler thread exactly the same. Also in switch. In fact, there's only one place where this happens in the code. In fact, when it switches to another, it actually calls switch too. And when this kernel thread actually switches back, basically, this switch will cause this switch to resume or get out and return from the switch call back into the scheduler, back into the scheduler thread. So it's basically sort of an infinite loop, calling switch. And when another thread is done, basically, the scheduler thread comes out of that switch and goes back and does its job. And so there's no random sort of you can imagine a thread switching plan where any particular point of piece of code could actually switch to another thread. That's not true in x86. It's a very stylistic way in which code switches happen. This style of programming is sometimes called coroutines. And so basically, the kernel threads. Switching between kernel threads is organizing the coroutine style. We'll look at it in a second and it will become more clear. The reason, other than maybe it's easy to understand the code, the other reason to do this is that it actually now much easier to deal with locks. So this thread's going to do in the car, And then this thread, when it comes out of the switch, is going to do a release. But before going back into, it's going to do an acquire again. But then when it might actually not go, to this resume this thread, it actually might switch to the first thread. But that thread, when it comes out of the comes out of the switch, will do a release. Right? So basically, even though the thread, one thread does the acquire, another thread does the release, it's sort of organized in a way around switch. The switch always basically gets locked beforehand and then releases at the other end. So it's reasonable and easy to understand actually what's going on. Okay? And this will become more clear, I think, if we'll look at the code. Then the final thing that actually will help the cleanup is the Unix API. This is the third technique that helps us in this cleanup. You remember when a process exits, does its state disappear? You remember it goes in a particular state. People remember what it's like? Yeah, it goes into the zombie state. It actually doesn't disappear. And the reason it goes to the zombie state, correct, because the parent process may have to call wait, or will call wait, hopefully at some point, and then return the return value of that process to the parent. And so that state has to be around anyway, and so it's already explicit in the interface that there is sort of a wait and exit. And so when a process terminates, it doesn't actually have to clean itself up. It has to wait, still sit around anyway until the parent calls wait, and then the parent, of course, can clean up the process at that point in time too. So that's all some of this synchronization problems. Does it all make sense? Get a reasonable idea what the... Okay, so let's look a little bit at actually how things work. So the first thing I want to do is, I wrote this super good program that it's very, very exciting. I'll give you a couple minutes or seconds to read this. So how many processes does this program create? Or the 2 for calls, correct? We start out with 1 process, and in the end we end up with 3 processes, correct? And what do these 3 processes do? Sit in the interval loop, correct? And so there's clearly not, there's not a very productive program. But our operating system shouldn't fail when running this program. So let's run the QEMU with 2 processors, correct? So we have 3 processes, correct, and 2 processors. And now we can run it, and we can look at the state, correct, and sort of see whether every process gets a chance to run. And if things are implemented correctly, then every process will run for some period of time. So here's how, we can't see anything, but there's a control P, correct, and we can look at like which processes actually are runnable. And we'll see some state about each process. We see 2 processes are in sleep. Presumably there's the shell is one of them, and probably the other one is in it. Then there's one process number 3 that is running. There's a process number 4 that's runnable, meaning it's not running currently on the processor. And then there's a process 5 that actually is running. Right? And so we hope that like this runnable sort of switches around between these processes as we sort of check once in a while. And we're lucky, that's the case, correct? And all 3 of them actually had a chance to run. Right? So clearly, you can't tell that correct from this what's going on because the processes don't do anything. But there's something interesting is happening because like clearly they can all get a different chance to run. All right? So we want to understand like why this is the case, right? And why how all the mechanisms that we talked about enforce this. So let's look at that. And we're going to quit this. Run it under GDB so that we can see actually how everything works. And so I want to set some breakpoints. So the place I want to, I'll talk about it in a second, but the places where I want to set a breakpoint, correct, is the code path where trap calls yield. Remember, like the clock interrupt, calls trap, and there is some statement in there saying like if you run out of your number of cycles, then you should call yield. And you've seen this in homework, one of the earlier homeworks. So I'm going to pick it up there. So I'm going to set a breakpoint in trap.c136.
An extra R there.
Oops. Thank you. 6. And going to continue. Of course, immediately going to get a clock, at the first clock interrupt, immediately you're going to see yield. I'm not so interested in that, correct, because I want to see what happens when hog is running. So I'm going to skip the first 100 of these breakpoints. This allows me to shell to get running, correct, because we're taking interrupts. So quickly type in hog, and boom, we're going to get a trap, correct? And so now we can look at the trap frame, just double check that this is actually the right process that we want to look at. And so let's do sort of inspection here. Does this look like a user level process to you guys? Well, easy way of deciding that, correct, is look at EIP, it's 90, right? So it's not a high address, so it's probably user level process. Right? Another way to look at it is at the CS. We'll see that basically the CPL level 2 bits are set. Right? So it looks like a user level process to me. So we can actually look at the proc state that goes along with it, correct? Because look at this code, correct, which particularly looks at the current process. Print whatever star executes 0 proc. And so here's the process structure, like in JOS, this is called the context or the environment, correct? Here it's called the proc structure, and we'll see what the proc structure is for current running process, and we see indeed it's a process called hog, and the process ID is 5. So it's like we have 3, 4, and 5. This is the third one of these guys, correct? Another thing that's interesting, it actually has a state, which is called running, which is not surprising, correct? Because it was running, and it got the clock interrupt. So from the x86 point of view, of the kernel perspective, this process actually was running on the CPU. So one thing that's interesting to do is to draw out what are the states in which a process can be. So let's do that first. So if we maybe go a long time ago, you remember that process starts, of course, proc structure starts in the state of unallocated, so it's not being used at all. And then whatever proc allocates it, and anybody remember in what state it actually is brought into? Yeah, embryo. Very good. The state embryo, basically, this is a state where the process is built up, the kernel is building it up. And then I'm going to take a little bit of time to do so. Then at some point, fork, fork finishes it off and actually sets it in a state runnable. This fork does this, and this is proc alloc. And then there's a couple of different states where it can be in. Once it's runnable, means that it's in principle ready to run, but it's not running. So this tells the scheduler, like, okay, here's a process that I could run. And so the next state that could go on is in the state running. And this is the scheduler that does this. Of course, when it actually gets where we're looking at this particular instant in time, correct, it's a process that actually is running. We want to stop it for a while, but it actually is runnable, right? And so at this point, what we expect is that after this yield, this process 5 is going to go to the state running, right? And where at some point, it actually might go back to the state running when actually, or there's going to be state runnable, and it will at some point go back to state running when there's a time slice available for that process to run. Now, the other state that the process can go into is sleep, if it is waiting for something. So it can go from running into sleep. Right? And this happens when the process explicitly asks, in the wait example, for a disk interrupt to complete or for a disk block read write to complete. And then wake up can put it back in the state of runnable. And we'll talk about these two transitions a lot more next week. Okay? And then there's one more. And once it's in running, and it actually calls exit, as we talked before, and we'll actually go to this state zombie. So exit. And we'll go to basically cleanup when actually the parent is called wait. So this is the sort of lifetime of the state diagram for every process. Does that make sense? Any questions about this? And so we have, so, yeah.
So when you go from sleep, there's no way to go from sleep to running. Like, there's always a transition to running.
Yeah, because there's no guarantee that there's a processor available for you to run on at the point you're coming out of sleep.
But if there's no runnable processors, but there's a process that's like done sleeping, it can't go away.
No, because running means you're actually on, so okay, the state running means you're physically on the processor and running. And so when you're like not sleeping and somebody else wakes you up, you transfer the process changes from state of sleep to run and wall. Because at some point the scheduler can now select to actually run it on the processor. Make sense? And so that's, again, this is typical, like any operating system will have a diagram like this. In fact, you will have a similar sort of type thing running in your library operating system, right, where you keep track of what, in fact, your scheduler that sits in the kernel in lot 4 will have also some state. Yeah.
So when going from running to runable, if it's like, let's say timer interrupt forces it to give up the CPU, does that mean it's the kernel that's actually calling yield as opposed to the user program itself?
Yeah, so basically what happens, right, like as I mentioned here, that basically it's the kernel thread, correct, corresponding to the user thread that actually calls yield. And we'll see, correct, in a second, hopefully when we look in the yield code, it will assess, the proc state from running into runnable. Okay? All good? Okay, so let's enter actually this function. So we single step into it. Hopefully, what I do. Okay. So the first thing you see is actually we're in yield now, correct? And the first thing it does actually grabs this lock, the process table lock. And that makes sense, correct? Because we, another scheduler or another processor, right? We're running one processor, calling yield to this processor, but some other code of this processor might be looking at the state of this process. Right? The scheduler on for example, the scheduler on another CPU might be looking at the process state to see actually if it can be run. And so we don't want anybody to touch the proc table while we're trying to modify it. And so the first thing we do is we grab the lock. This will make sure that nobody else or no other processor will be manipulating the process table. Okay? So you know all about acquire and release now, so I'm going to skip that part. And you'll see here, correct, that the next thing it exactly does actually it change, yield change the state from running to run. No surprises here. And then the next thing that actually happens, we're going to go to sket, and this is presumably where this point in the code is where we're going to switch from one kernel thread to sket. So the sket basically is when the kernel thread, a function that calls to actually context switch from the current running kernel thread to the scheduler thread. So this is interesting, so we're going to go into it. And it does a couple things. It does a couple of checks. These are mostly checks, for us to debug things, because there's actually, even though we try to make it as simple as possible, it's still pretty tricky code. And so there's a bunch of checks here that will just check things. And one of them actually, I'm going to just point this out. The panic that happens for the homework assignment for the file table lock, this is the panic that's going to go off if you do the store interrupts in file L. So I'll talk a little bit about that later, but just to flag for you where it actually sits. And so, of course, so we're going to walk through this function a little bit further. So it checks if it's a process state running. Clearly, it shouldn't be, correct? That would be an internal invariant that is not true. We expect it to be not running at this point. So we'll check that. And not that interesting. We also check a little bit about the eflex. But this is all stuff just to double checking that our code is correct. And it presumably still has bugs, but maybe fewer bugs now these checks pass. Okay, so then the interesting thing actually is the switch function. So the switch function actually does, we've seen this switch function before, right, where we actually do the actual context switch. And remember, the way that worked was as follows. So I'm going to keep this. Every process, right, has its own stack, kernel stack, and I'm just going to draw the stack somewhere here. and associated with a process, so we have a proc table entry, where it's run all, correct, it's one of the entries, and another entry is like the top of the stack, and an SV, and then there was this thing called a context, which is a pointer on the stack. And what we're going to do, like what this switch function does, it actually pushes the state of the current running thread onto the stack. And so what do we expect to see there? Since you're pretty good at context switching at this point, so like what do you expect the state to be saved? Yeah, all the registers, correct? And presumably what we're going to, so let's go, and presume what's, so this process is going to basically save, the switch is going to save the state of the current running thread in this proc context switch, in the proc context structure, correct? And basically what's the structure that's overlaid on the stack. So here's our context. Standard trick, like same as like the trap frame. And basically it's going to load, from the CPU scheduler, the CPU thread, its context. And so presumably what will happen is that if we come out of switch, do you think that the next function will be this the next instruction that will run? If we come out of switch? No, presumably we're going to come out wherever, what is the safe EIP that sit in the CPU context, correct? And presumably that's somewhere in the scheduler. Right? But remember, we're still holding the p-table lock. Right? And so why is it actually important that we hold the p-table lock? Actually, we can answer this question right now. Even like with these three instructions that we looked so far, if we had not be holding the p-table lock, we already have a race condition.
To make sure that the scheduler thread is only running once.
That's one reason. That's actually the scheduler thread actually runs or may already be running, or at least on another processor there might be a scheduler thread running.
Sure, but not concurrently.
Not concurrently. Well, concurrently on another processor, but not on the same processor. So what dangerous thing do we do? Look at this. Like there's one dangerous statement in yield, correct, that we did. We set the proc state to runnable. So what is?
So like we could try to like run the same process on like two different CPUs or like.
Yeah. So if we had two CPUs, correct? We had another CPU here. And here's the scheduler thread running in that CPU. What is the scheduler thread going to look at? Well, it's going to look at the process state to decide whether something is actually can be run, correct? So see, as soon as this thing we set to runnable, in principle, the scheduler thread could look at it. And luckily it can't, correct, because we're protected by the lock. And the scheduler thread presumably also takes the lock out of the P table. And if this process, this thread got it first, the scheduler thread won't do anything, right? It will be spinning on the lock until that lock is released. But let's say that lock statement was not there, correct? Well, what would happen, correct? As soon as that scheduler thread on the other processor would see that this process is runnable, and decide, well, I could run it, right? And that would be a complete disaster, right? Because now basically the same thread is going to be running on two different processors, and one processor is like exiting, switching out, and the other processor is going to be switching in. And presumably this is going to get, huge amount of problems, correct? The problem doesn't work out correctly. I don't exactly know what happens, but I presume this is not going to work. It seems ripe for problems. Certainly the semantics is broken of having two threads running. There should be an invariant, correct? That a thread runs at most at one processor at a time and not at two at the same time. So it's crucial that we hold that lock because we need to finish our context switch. Does that make sense? So this is one reason why this sort of context switching code is complicated, because there's locking invariants going on at the same time that you're doing this tricky context switching. Okay, so let's go to switch and we'll just see where we end up. And no surprise, correct? We went through this function a little bit before. We're going to put the arguments into two different registers. Then we're going to save the registers of the current thread. Boom, boom, boom. And then we're going to switch stacks. So we're going to take the stack of the scheduler thread and put it in the stack pointer register. And then we're going to pop all its state from its context into the registers of the processor, correct? And so there we go. And the last one, presumably ret, what was ret pop off? To save the IP, correct? And so presumably this is the point where we're going to come out of this context switch in the scheduler thread and we're going to end somewhere. So let's see where we end. And we're basically writing this piece of code that's in the middle of the scheduler. Right? And we see actually, how did the scheduler actually get into there? Well, it called a switch from with saving its state into, and then to this current thread where we just came out of. Right? And so this is this coroutine style where basically we're always switching, between very specific points between two threads. In fact, the scheduler thread, the only place where it switches between two threads is actually here. So let's look a little bit more in detail. So here's the complete scheduler code. It's basically a for loop, correct, that runs over the proc table, looks at runnable, and then decides whether something needs to be run. Right? And you're going to implement something very, very similar to this in Lab 4. And some of them might already implement it. And so, but notice, when we came into this function, actually the scheduler thread has to lock on the p table, correct? So it's completely safe for it to sort of go back, go to the top, and run over the p table process table, because it actually holds the lock for basically giving it an approval to actually run out to look at the process table. Make sense? And presumably what's going to happen on the way out, correct, when we switch to another thread, we still hold the process table lock. We'll complete the switch to this new thread, and that new thread is in charge of releasing then the process table lock. And because of this coroutine style, it actually works out perfectly. Right? Every require matches up with one release. And I can tell you, we tried a long time to do it without a scheduler thread, and not in coroutine style, because we thought it was lame that you had to do two context switches. But code is so complicated. Almost works perfectly, except in this one case, correct? When something goes wrong, for example, thread wants to exit, and we don't really know how to get it exactly right. So this is way simpler. It may be hard to appreciate when you didn't do it wrong first, but it is. So it switches to the. I will go back here. So we're going to go run the loop basically a bunch of different times, correct? So let's look at the scheduling policy. It's going to go to the top. And it's going to look at for the next runnable thread. Now let's look at this for loop. What scheduling policy does it implement? So one question we could ask, this thread that we just say timed out, correct? The hog that has run for its complete 100 millisecond time slice. Is it likely that it's going to get run immediately again? No, correct? Because we're actually taking off. We just got back and we just the p pointer, correct, is pointing actually to this particular thread, and we just passing one beyond. So if the proc table has all threads in it, correct, so here's the proc table, it's going from 0 to whatever some number n. Here was our hog 5, correct, and basically we just increase the pointer to past this, correct. So at least we're not running the same hog immediately again, and that would be a mistake, correct, to do so. In fact, it's a mistake you should not make in Lab 4 either. Have to write this code. So what's the scheduling policy for this piece of code? Yeah, it's round robin, right? It just goes around. So round robin refers to the policy there. You basically give every thread an equal chance to run. If the thread is running, you get it running. So clearly, there's a very simple policy to implement because it takes one line of code to implement it. Right? Real operating systems, do they implement round robin? You sort of do implement round robin with a lot of additional machinery. So, like, what are the things what you might want to have in the scheduling policy that this code doesn't really implement? Sorry?
Preventative process from being started.
Well, so our policy is pretty good in terms of preventing a process being started, right? Because we're actually always going around. We always start at the beginning. Then there would be a chance that we would start some process, right? Because we never get a chance to run. But we nicely go around. So every process gets a chance to run.
Well, sort of like if all the process, let's say one process always does like nothing, and then one point it decides it wants to do a lot. Then now it's something limited by it.
Yeah, so it's certainly the case. Like once a process gets to 100 milliseconds, it can run for a complete 100 milliseconds, right? And if the process doesn't do much, and it gets, basically, and other processes get the processor back quickly, then these other, there's one, process that's badly written gets actually way more CPU time than the processes that are actually behaving well. So what we might want to do is punish, the process that actually is, misbehaving, right? And one way to do that is to implement priorities. This is a very common thing to do, where you basically you lower the priority of the process that, for example, is not behaving very well. And then this for loop would be slightly different, correct? And the selection criteria would, well, we'll pick the highest priority process first, and then we'll run the next level hybrid, and we'll round robin within them, etc. Another reason you may want to do priorities is, for example, if you have an interactive thread, like some thread that's running the shell. It would be pretty annoying, correct? If, like, let's say the shell was this program. Correct? Then the way it would go, correct, if we go for this proc structure, that every process in principle behind it is going to run first for 100 milliseconds, go around, those guys run for 100 milliseconds, and then finally the shell is turned on, correct, if all of them are runnable. So if we had 100 runnable threads, the shell had to wait 99 times 100 milliseconds before it actually got to run, correct? Is that going to feel very interactive? Not at all, correct? And so basically all schedulers try to improve interactivity by, for example, giving I/O-driven processes higher priority. Because the shell is probably going to run actually for a very, very short period of time. Right? What's the shell going to do? It's going to maybe wait on this process. It's going to do the wait, and then like type in a command, and then it runs the next process, and it's going to wait. So in fact, the amount of time that the shell uses is extremely small. So it seems fair to reward it for giving the process back quickly, that at some point later, it actually gets to the process with higher priority than other processes. So you start thinking about this, right? About scaling policies, there's sort of a bunch of conflicting goals, right? Like high interactivity means low latency. On the other hand, you want high throughput. Like you want to be applications that can run for a long period of time and cycle a lot, because every time you run the operating system, correct, that's basically overhead. And so there's an advantage of making the time slice very, very long, right? Because then you have to context switch once in the, say, instead of 100 milliseconds, you might have to context switch once in the, whatever, 1,000 milliseconds, right? So there's a whole bunch of conflicting goals. And so if you look at a typical operating system, you'll find that the scheduling policy they implement is quite complicated because they're conflicting goals, and they're sort of trying to weigh all these conflicting goals and they come up with some reasonable policy. And so in fact, there's a literature on scheduling policy that dates from the early 60s and is still active. So you can go to an operating system conference, as we did last week, and you will find scheduling papers. Very few of them are very interesting. Because basically it's a set of conflicting goals. They're insurmountable, like conflicting, and so you have to make some set of trade-offs. And once in a while, there's a scheduling paper that has a brilliant idea, but most of them are like, we should give a little bit more weight to this decision versus that decision, or something like that. All right? And so, if you're really interested in this, and we could spend probably the rest of the term talking about scheduling policies. I personally find it quite boring. So I'm not going to do that. I find the mechanisms much more interesting. So now let's see actually, the scheduler is going to run, it's going to look at this queue, it's going to walk through this whole proc table to get back to actually get a process that we want to run. So let me set actually a breakpoint at the point that we are hopefully going to run something interesting again. So we're going to set a breakpoint at proc.c. Continue, and so the scheduler has run around, correct, and actually has found the process that is actually runnable, and it's going to now switch to it. So we want to look, see what the second part of the switch happens, correct? We have done this part of the switch, now we're going to see actually the other part of the switch, which is basically it's pretty straightforward, but that's worthwhile looking at. So, first of all, we're going to switch the virtual memory system, correct? We're going to now switch to the virtual memory system of the destination application. So we'll do that, but we'll skip that. We know how to do that. And here, the thing is set to running, correct? And so this is all good because we still hold the P table off, right? So there's nothing really wrong here. We'll do that, and then we're going to go back into switch. Right? So let's go back into switch, single step, and then we'll do exactly the opposite, correct? We're going to go from the scheduler, we're going to save the scheduler's context and switch to the destination thread context. We don't know what the destination thread is at this point because I didn't look at the proc structure for that particular thread, but we'll find out soon enough. So let's single step for this, and basically it's the same piece of code that we saw a second ago, but exactly the other way around. We switch stacks, we pop some registers, but now we're starting to pop the registers from the destination thread into the registers of the processor, with more, and up, more. And now red, correct, is going to, somewhere on the stack is the EIP of the instruction, of the next instruction that we need to execute for the thread that we're going to go to. Right? So at the point that we're doing a red, something magic happens, we're going to switch to another piece of kernel code. Right? So single step, and boom, we're somewhere. And where are we? Well, this looks very familiar, hopefully. We're back in Sketch. Right? So this is this coroutine thing going on again. And so let's finish this. So we're going to single step here. We're going to go out. And the fact that we're going to come out of yield. Right? This is exactly the place where we actually gave up the processor, and now we're back in yield. But in the meantime, correct, between these two instructions, remember what I told you about earlier in the beginning of the class, that when you see two instructions next to each other, that doesn't mean that they're going to be run one after the other, correct? Because between these instructions, how much code has run? Like the whole world changed, correct? Virtual memory system has changed, the processors changed, the proc structures changed, we implemented scaling policy, like thousands of cycles of stuff happened, between these two instructions, right? And so, but we're happily back here, and see the first next thing that actually yield does, that actually releases the, let's actually complete that, and releases the process table block, right? Because the whole context switch has happened now, we're in very good state. So now we can actually print whatever CPU 0, 0. Proc, and we're running a new thread, and it's quite exciting. We're running another hawk, but this is number 3, right? And now we'll return to user space, and we'll now get 100 milliseconds, to run until the next time slice, time interrupt comes in. Okay? Does that make sense? Yeah. Question, good. Yeah, thank you.
Yeah, so you set proc state to runnable before you call the scheduler. Is there any reason to do that as opposed to the other way around? Is it possible for the scheduler to then call the same process that just stopped?
Okay, so the question is like, why do you set proc state to runnable before we call schedule? Because there's different ways of getting into the scheduler, which I'll talk about next week about. Like sleep will also go call this function, but instead of saying proc state to runnable, we'll actually set it to sleep. And so it actually, the caller actually has to determine what its state is. And if it's not the scheduler, it cannot determine that. If it almost is the case that like the way you would get to the scheduler was through yield, then the scheduler could set the state to runnable. But that's not the case. You might actually get through sleep and wake up to the scheduler. So it has to be the case that the caller has to set the run state. But then it means also that the block has to be acquired. Yeah.
So this is kind of mind-blowing, but basically, so you're in like the same code that you were in with call sketch, but you're in like a completely different thread now.
Yeah. Isn't it awesome? Yeah, I never know what to think about this. Like on one hand, I think this is so simple, right? Like nothing really happened. We switched some stack pointers and we popped and pushed some state. That's all we did, correct? In fact, but if you think of a bigger picture, like the world has changed, correct, between these two threads, between the two machines. So I never remember. I was conflicted about this. Is this a boring lecture or is this a very interesting lecture? And I'll leave it up to you to decide. But as I said, like the first time you see this, it's like magic, but it isn't. Do people get a little bit of sense of what actually went on? And you're going to do this in lab 4 too, correct? So you will get more and more. You'll start appreciating it a little bit better. But, yeah, I don't know what to say other than, sort of, I think this is very similar to things like recursion, and like you see it the first time, it's sort of like magic, but then you start using it quite a bit, and then you're sort of like, oh yeah, it's obvious. Why did it take so long to understand recursion? I don't know. But, yeah, sorry.
So where in the code is it actually starting just after the hog?
Sorry, I'm not sure what.
So in the picture you drew up there, you mentioned that to do the round robin, we're starting our search for a runnable just after the thing that got made runnable?
So presumably what happens is there are only 5 processes in the process table at this point, correct? If you remember from control P that I did, like there were 5 processes, 2 of them were sleeping, numbers 0 and 1, and then 3 and 4 were runnable. Those are the 2 auto hops. And presumably they're right before 5. So the picture presumably, if I'm super good, I would guess that the picture is something like we have 2, so here's hop 4, here's hop 3, and here's the shell, and here's N. And this is 0, this is 1, and this is 2, 3, 4, and of course the process IDs are slightly different. That's the index in the practice.
Sorry, so I guess in the code, where is it that you're setting that loop to start just after the current one?
Okay, well, so looking back at that, actually we didn't do anything. This is the most interesting part of it. We didn't have to do. Oh, naming process. No wonder it is. Man, I'm today. Today's not my typing day. Oops. So if you look at the loop, correct? When the next time around it comes out of the loop, out of the switch, where's P pointing to? Well, P is pointing to the current structure, correct?
It's still the same loop, okay.
Same entry, yeah. So when it comes out, it just goes to the next one. Of course, it might be a slightly different one because we might have already run through scheduler again for some other, thread, correct? Because there's another scheduler thread looking at the same entry, correct? And looking at the same proc table. But when it come out, it will always point to the current thread's entry. And so the next entry we'll look at is the next one after the current thread. Because basically every processor stores away the proc pointer to the current processor, to the current process that is running. It's called current proc. You will do something similar in Josh. You will have sort of the current environment that you're running, and so you have a pointer to that environment. So when you come back into the kernel, you know actually which environment you were running. Okay, so let me, this is all, so one more level of sophistication as an answer to this homework question. So, okay, so I'll tell you what goes wrong. So if we put store interrupts, right after the require, correct? This was the file alloc. What will happen is that we're going to break an invariant in the kernel. Namely, we're breaking the invariant that this particular assert and yield is going to go off. Oops, where is it? I guess it's in Sched. The Sched is called all over the place. Here we go. So this invariant is going to give us trouble. If we file alloc, what will happen? We'll enable interrupts again. Then what will happen, correct, there will be the timer clock will at some point go off. That will call yield. The yield call will come here and see that the number n client interrupts is actually unequal to 1. It should have been 1 because it's saved, like it did an acquire, correct, the file table lock. That acquire sets it to 1 to save 1 clear interrupt. And so then when it come in here, it will be 2. And so that this basically our invariant checking code will basically panic. And so the sequence that goes wrong in the file alloc case is basically you might be unlucky, correct, in this very short period of code. And this is what goes back, I guess, to the main theme of this lecture. A lot of surprising things happen. Like in this very sequence, you could get so unlucky, which just happened to this one student who's not here today, that after the acquire would do the interrupts you set on, and we could be unlucky that between this line of code and that line of code, or this line of code and that line of code, there could be just the timer interrupt could have gone made. Right? And that timer interrupt is going to call yield if it was the end of the time slice, and then it will panic in that particular invariant checking code that we have. Now, none of you have seen this, right? But clearly it's a bug. And this again signifies like how tricky concurrency is, right? Because basically, even though we said it unlikely, if it was a true bug, right, every one of you should have seen it. But it almost never happens because it has to be exactly the timing has to be right. It's so timing dependent that most likely you won't see it, particularly when only during boot up, because how many clock interrupts are you going to get during boot up? I'm still amazed actually that this one student saw it. Yeah.
So it seems to me like ntry, it's sufficient for ntry to just be not 0, right? We just want interest to be stable. Why does it have to be 1 specifically?
Because we wanted to be cool. Because unlike in JOS, x86 allows you to take interrupts in the kernel. And so you could have an interrupt, and even during interrupts, you sometimes can take interrupts. And so that means that you could have recursive calls, correct, to enable and disable interrupts. And you have to keep track how many times levels you're in how many levels deep you're into switching and turning off interrupts. And basically, ntry sort of counts the number of CLIs that you need to do to get back to the corresponding STIs that you've done.
But why is it variant that it has to be 1?
Oh, because in this particular sequence of code, it has to be 1. Because there's no, I think you're running out of, okay. At the point you enter yield, you should not, all interrupts should be cleared. And you should have not done any recursive interrupts. But you do have the lock in your hand. You should, the really invariant that we're checking is that you have the lock in your hand.
So presumably that could be fixed by just introducing another flag that the CPU structure has.
You can.
That's like, the file info lock is taken, don't raise as an extra 0.
Yeah, no, there's many ways of doing this, correct? In fact, you should basically, these are like our invariant checking code, and you should ignore our invariant checking code, right? It should be just correct, period. And so this is one way for us to check things, but you could check it in other ways. And I mean, clearly, the reason all this invariant is like one of the few functions you probably noticed that has a lot of this invariant checking code in it. And the reason is because we had so much trouble getting this right, right? And the reason I think we're not sort of reasonable confident about it is because of this coroutine trick, organizing things in coroutine, introducing a scheduler thread, a separate scheduler thread, and having this very precise protocol for who does the acquire and who does the release. And between the three, we feel like you can, at least I feel like I can lecture now and explain to you why this code is correct. If we hadn't those mechanisms, it'd be very, very hard to, given correctness argument, and you would be probably even more mystified about like the magic that's happening here. All right, well, have fun implementing this in Lab 4.